Okay, this is Mr. Gieske going to talk about proving trigonometric identities. I think the first thing to take a step back to about trigonometric identities is to distinguish prove, solve, and simplify. Those three instructions are often given on math problems, and I don't think students do enough distinguishing among the three. I think doing so will help understand how to work with trigonometric identities. So to prove or to disprove, those are the in green here. To prove something is to demonstrate its mathematical truth in all cases. And if you like to disprove something, you just need to demonstrate a falsehood in one case. So this is the hardest work I think that mathematicians do, is try to prove arguments or theorems or lemmas or whatever. What they're trying to do is establish just how far, just how many conditions they must describe so that something is true all the time. Okay, the next thing that you see a lot is to solve. To solve is to describe conditions that will make truth. So recognizing that some statements are only true for certain conditions. To solve is to describe those conditions. So for example, the statement x plus 7 equals 10 is only true when x is equal to 3. So when you say solve x plus 7 equals 10, you're describing the condition x equals 3, which is required to make x plus 7 equals 10 true. So it's sort of like a conditional statement is what you're given, and to solve it is to say, well, these are the conditions that make it true. And then finally, you get instructions to simplify. This is quite different because an expression, a mathematical expression or mathematical statement, doesn't necessarily involve a verb or doesn't involve a verb. So the statement, x plus 3 over 2x doesn't have a verb in it. It doesn't have an equal sign or a greater than sign or a not equal to sign. It's just it doesn't have a predicate. It's just a mathematical expression. And to simplify it, you might say this is x over 2x plus 3 over 2x, and that might be considered to be 1/2 plus 3 over 2x. Now the difficulty with simplification is that sometimes the final statement doesn't look simpler than the first statement. I would say that maybe this one's simpler than the statement. But so simplify sometimes means just change, rearrange, re-express in a different way. But to distinguish it from solve and prove, you're basically working with a statement that doesn't have a verb in it, and you're just trying to re-express it in simpler or sometimes just different form that's not always simpler. Okay, and then finally, what is an identity? Well, an identity is an equation that's always true. Okay, so for example, 10x is equal to 7x plus 3x. That statement's true for all values of x. You cannot think of a value of x that doesn't make that statement true, which makes that equation an identity. The solutions for this equation are all x. So there's no special condition that you need to describe to make the statement true. It's an identity. So therefore, identities are proven or disproven. To prove them, you need to show that the statements are totally equivalent on one side of the equal sign and the other side of the equal sign. To disprove them, you just need to come up with one value or one condition which makes that statement untrue. So the instructions for working with trigonometric identities is always prove or sometimes disprove. The harder work is to prove. So how do you go about proving a trigonometric identity? Okay, so the symbol that you're trying to prove is this one right here, the equal sign. Your instructions are, is that equal sign always true? That's the question. And to answer it, you may not presume that the equal sign is true. So you can't use any theorem or rule that presumes that the equal sign is true. For example, you cannot add something to both sides of this supposed equation, because to add something to both sides of the equation is to use this statement. If A equals, if A equals B, then A plus C equals B plus C. Notice the if. If A equals B assumes that the equal sign is true. If you're trying to prove that the equal sign is true, you can't start with a statement that begins with assume the equal sign is true. So not only can you not add things to both sides of the equation, you cannot divide things, you cannot subtract things, you cannot multiply things to both sides of the equation. So a lot of teachers say it's like you've made a brick wall here. You can't cross. But that's a little reductive. I mean, it's fine to remind yourself that there's like a wall there, but the truth is, or the way to think about this is, my equal sign is in question. I cannot use properties of equality. What can you do? Well, you're allowed to express these statements that don't involve an equal sign. Tan x times sine x plus cosine x is a mathematical expression, and secant x is a mathematical expression. You can re-express those, simplify those, with the hopes of maybe creating equivalent statements. And if you can make equivalent statements, then you've proven the equal sign is true. So let's try that. One thing I always advise my pre-calc students when working with these is the first thing to do is to re-express everything in terms of sine and cosine. So tangent of x is equal to sine x over cosine x. Then we have sine x here, multiplied by that, plus cosine of x. And on this side of the supposed equation is 1 over cosine x. So if I can somehow make the left side look like the right side, then I've done my job. So how can I make this look like this? Well, it looks like I've got sine squared x over cosine x plus cosine x. And now I've got really like cosine x over 1. And I've got an addition, so I need to add these fractions, which involves finding the common denominator. The common denominator is cosine x. So the common denominator is cosine x. The numerator of this part stays the same. And I must multiply the top and bottom of this fraction by cosine x to get a denominator of cosine x. So this becomes cosine squared x. And then I've got a Pythagorean identity that says that sine squared x plus cosine squared x is equal to 1. So 1 over cosine x here. And I've got down over here 1 over cosine x. And these two statements are true for all values of x. These two statements are equivalent for all values of x. So now I've shown that these two things are equal, and I've got a true trigonometric identity that presumed nothing about this statement being equal. Okay, let's try a harder one here. I think that when you look at this problem, a lot of students will try to mess with this fraction. A mistake is to say that tangent squared x over tangent squared x plus 1 is equal to tangent squared x over tangent squared x plus tangent squared x over 1. And that's not true. That's not an algebraic statement you're allowed to make. It's just not true. So 3 over 5 plus 7 does not equal 3/5 plus 3/7. Okay, that's not the case. What is allowed is 7 plus 5 over 3 is equal to 7/3 plus 5/3. That's a common denominator. There's no such thing as a common numerator. So this is unfortunately not allowed. So what do you do? Well, I would suggest transforming this into sines and cosines. So sine squared x over cosine squared x. That's equivalent to tangent squared x. So I'm going to change that into sine squared x over cosine squared x down here too. Okay, and then I've got this is still supposedly, I'm going to circle it again, equal to sine squared x. So if I can make it equal to sine squared x, I've gotten my job done. A lot of students, when they see complex fractions like this, just really get the heebie-jeebies, and I don't blame you. So what I'm going to do here is to eliminate the complex fraction by multiplying the top and the bottom by the denominator of the fractions in the top and the bottom. So if I multiply the numerator by cosine squared x and I multiply the denominator by cosine squared x, I can divide this factor with this denominator. And this factor is going to divide with this denominator and then multiply by cosine. This is a totally legal move. It doesn't presume the equal sign is true. I'm just multiplying the fraction on the left side by a form of 1. And it's a good choice of form because it enables me to rewrite my expression in this way. Sine squared x over, this is going to be sine squared x plus cosine squared x. Okay, so again, the division looks like this. I can divide this factor with this factor, and then in the distributive property of the cosine squared x across this term plus this term, this one divides off with this one, and then it distributes to the 1. Okay, so then finally, I know that there's a trigonometric identity that says that sine squared x plus cosine squared x is equal to 1. So the denominator of this fraction is 1, and I've got sine squared x. And remember my little wall that came down here, this is equal to sine squared x. So this identity is always true for all values of x. Okay, one more here. I chose this one because it doesn't have the squaring involved, and also it doesn't have much in the way that needs to be changed into sine and cosine. So this got me thinking about why these things trouble students so much. There's just lots of options when you're working with identities, and it really tests your ability to work with algebra, and I think that's really the issue. So there's nothing to change the sine and cosine except for the 2 tan x on the right side. So I will do that first. I'll call this 2 times sine x over cosine x. And that's really the only quick and easy simplification to make into sines and cosines. So the left side now is really presenting me with something to do. So I'm going to work on it. What is there to do? I would say to make a common denominator. And the common denominator is the product of these two relatively prime denominators. So 1 minus sine x on this side times 1 plus sine x on this side. If you need to review how to work with rational expressions, I made a video on that. You can check that one out. But to get the denominator of this, for this term here, I need to multiply by 1 plus sine x. So, sorry, 1 plus sine x over 1 plus sine x. So that's what I'm going to do to this one. I'm going to multiply it by 1 plus sine x over 1 plus sine x. So I get go back to green. I get cosine x times 1 plus sine x. And then I have a minus sign here. And this term over here, I'm going to multiply by 1 minus sine x over 1 minus sine x. So I get minus cosine x times 1 minus sine x. Okay, so that's my new expression for the left side, and that's pretty complicated, but I'm hoping that it boils down to the expression that's written on the right side. How do I get there? Well, I need to use the distributive property, another troublesome spot for some students. So I multiply the cosine x across this fraction, this factor, and I get cosine x plus sine x cosine x. And I multiply the cosine x across these two, recognizing it has a minus sign in front of it, so it's going to be minus cosine x plus sine x cosine x. And this is still all over the fraction 1 minus sine x, 1 plus sine x. Sorry, 1 over the denominator there. Okay, so then I'm going to combine like terms, and I see that cosine x minus cosine x is going to subtract away. I don't use the word cancel because they're just subtracting. Okay, so I get 2 sine x cosine x over 1 minus sine x times 1 plus sine x. And I'm looking at this right side and I'm like, oof, okay. Well, the progress I've made here is that I have the 2, that's good news, and I have a fraction, Instead of having two complicated fractions here, I've got one fraction that has a 2 in front of it. So progress is being made, but somehow sine x cosine x is over 1 minus sine x times 1 plus sine x is equivalent to sine x over cosine x. I'm wondering how that's going to work out. So I'm just going to pull the 2 out, and I'm just going to follow my nose here. I'm going to do what's offered to me. What if I FOIL these guys? Well, that looks like a difference of squares. When I have a minus b times a plus b, that's just a squared minus b squared. So that's going to be 1 minus sine squared x. That's kind of familiar. Sine squared x, 1 minus sine squared x. There's an identity that says that the cosine squared x plus the sine, it's usually written the other way. It's usually written sine squared x plus cosine squared x always equals 1. That means that sine squared x is equal to 1 minus cosine squared x. And it also means that cosine squared x is always equal to 1 minus sine squared x. So those three things are the same, and they're always true. These are one of the Pythagorean identities. So I can re-express this as 2 times the quotient sine x cosine x all over, now 1 minus sine squared is equal to cosine squared. Okay, looking better and better here, because now I recognize that this cosine and one of the two factors of cosine in the denominator will divide. So I'm left with 2 sine x over cosine x. And I look up, and lo and behold, that was what I was looking to get equivalent to. So once again, that's an identity that's always true. Now, a lot of times students say, well, how in the world did you think up that? And to be honest, all I did in this problem was pretty much follow my nose, and my algebra is good enough for me to sort of carry me downriver. So by that I mean I was able to create a common denominator here without making a mistake. I was able to combine like terms and distribute without making a mistake on the negative sign. I simplified and just hoped and prayed that I was getting there. And sooner or later, it got looking more and more comfortable, and I got looking more and more confident, just following my nose with the algebra, and suddenly I got to the final step of the proof. So it's not like there's a knowledge beforehand of what's going to happen. I'm just sort of taking what's offered to me, doing good algebra, and then chipping away and finally getting to the final solution. That's often the mentality that you have to carry into doing trigonometric identities. Okay, I hope that helps. Good luck.